The universe we live in appears familiar at first glance. We see stars in the night sky, planets moving across it, galaxies shining faintly in the distance, and all of it feels like a vast but understandable system built from matter we can observe. For centuries, humans believed that everything in existence was made from the same basic ingredients that form the Earth, the Sun, and the stars. The idea was simple. If something exists, it can be seen, touched, or measured in some direct way. But as science advanced and telescopes grew more powerful, the universe began to reveal a deeper and far more unsettling truth. A large portion of what shapes the cosmos cannot be seen at all. It does not emit light, it does not reflect light, and yet it is everywhere, holding galaxies together and shaping the structure of the universe itself. This mystery begins with a question that should have been simple to answer. What is the universe made of? Astronomers expected that when they added up all the stars, planets, gas clouds, and dust in galaxies, they would account for all the mass required to explain how galaxies move and behave. But something was wrong. When they measured the motion of galaxies and the speed at which stars orbit within them, the numbers did not match what visible matter could explain. Stars at the edges of galaxies were moving much faster than expected, so fast that they should have been flung into space if only visible matter was responsible for their motion. Yet they remained bound, held in place by something invisible. This discrepancy marked the beginning of one of the greatest scientific mysteries in human history. If the visible matter was not enough to hold galaxies together, then something else must be providing the missing gravity. This unseen component became known as dark matter. The name itself reflects its nature. It is dark because it does not interact with light in any observable way, and it is matter because it behaves like a substance that has mass and creates gravitational effects. But beyond these basic descriptions, its true nature remains unknown. The idea of invisible mass was not immediately accepted. At first, many scientists assumed that the measurements must be wrong, or that something about the motion of galaxies was being misunderstood. But as more observations were made, the evidence became stronger. One of the first major clues came from studying spiral galaxies. These galaxies rotate like giant cosmic pinwheels, with stars orbiting around a central core. According to known physics, stars farther from the center should move more slowly, much like planets in our solar system, where outer planets take longer to orbit the Sunday. But in spiral galaxies, something surprising was observed. Stars at the outer edges were moving at nearly the same speed as those closer to the center. This unexpected behavior suggested that there must be additional mass spread throughout and beyond the visible edges of the galaxy. Otherwise, the outer stars would not have enough gravitational pull to maintain their fast orbits. This unseen mass was not concentrated in stars or glowing gas clouds. Instead, it formed a vast, invisible halo surrounding galaxies, extending far beyond what telescopes could detect. As astronomers studied more galaxies, they found the same pattern repeated everywhere. Whether looking at small dwarf galaxies or massive galaxy clusters, the visible matter was never enough to account for the gravitational effects being observed. Something large and invisible was clearly shaping the structure of the universe. This realization forced scientists to rethink their understanding of cosmic architecture. Dark matter does not interact with light or electromagnetic radiation, which is why it cannot be seen directly. It passes through ordinary matter without being absorbed or reflected. This makes it extremely difficult to detect using traditional instruments. However, its presence can be inferred through its gravitational influence. Just as wind cannot be seen but its effects on trees and buildings can be observed, dark matter reveals itself through the way it bends space and affects the motion of visible objects. One of the most important discoveries supporting the existence of dark matter came from studying galaxy clusters. These are massive structures containing hundreds or even thousands of galaxies bound together by gravity. When astronomers measured the total mass of these clusters based on visible matter alone, they found that the galaxies were moving too quickly to remain gravitationally bound. According to calculations, the clusters should have been flying apart, yet they remained stable. This stability could only be explained if a large amount of unseen mass was holding them together. Further evidence came from a phenomenon known as gravitational lensing. According to Einstein's theory of general relativity, massive objects can bend the path of light passing near them. When light from distant galaxies travels through space, it can be distorted by massive structures along the way. By studying how this light bends, scientists can map the distribution of mass in the universe. What they discovered was surprising. The regions where light was most strongly bent did not always match the locations of visible matter. Instead, they revealed large concentrations of invisible mass, again pointing toward the presence of dark matter. Despite these strong lines of evidence, dark matter remains one of the greatest unsolved mysteries in physics. Scientists do not yet know what it is made of. It does not appear to be composed of ordinary atoms like protons, neutrons, and electrons. Instead, it may consist of entirely new types of particles that have not yet been detected in laboratories on Earth. Many theories have been proposed, each attempting to explain its nature. One possibility is that dark matter is made of weakly interacting massive particles, often called WIMPs. These hypothetical particles would have mass, but would interact so weakly with normal matter that they would pass through it almost undetected. Another idea suggests the existence of axions, extremely light particles that could fill space in vast quantities and create the gravitational effects observed. There are also more exotic theories that propose modifications to our understanding of gravity itself, suggesting that perhaps gravity behaves differently on cosmic scales than we currently believe. However, despite decades of research, no experiment has definitively detected dark matter particles. Large underground detectors have been built to capture rare interactions between dark matter and ordinary matter, but so far the results remain inconclusive. Particle accelerators like the Large Hadron Collider have also searched for evidence of new particles that could explain dark matter, but nothing has yet been confirmed. While dark matter dominates the gravitational structure of the universe, it is only part of the story. There is another, even more mysterious component known as dark energy. Unlike dark matter, which pulls things together through gravity, dark energy appears to push the universe apart. It is responsible for the accelerated expansion of the cosmos, causing galaxies to move away from each other at increasing speeds. The discovery of dark energy came much later, during studies of distant exploding stars called supernovae. These supernovae act as cosmic markers, allowing scientists to measure distances across the universe. When researchers observed these distant explosions, they found that the universe was not just expanding, but that the expansion was speeding up over time. This was completely unexpected. According to existing theories, gravity should be slowing the expansion down, not accelerating it. To explain this acceleration, scientists introduced the concept of dark energy, a mysterious force or property of space itself that drives galaxies apart. While dark matter pulls the universe together, dark energy pushes it apart, and together they shape the overall structure and fate of the cosmos. The realization that most of the universe is made of invisible components changed everything. Ordinary matter, the kind that makes up stars, planets, and living beings, accounts for only a small fraction of the total cosmic content. The rest is divided between dark matter and dark energy, both of which remain largely unknown. This means that everything humans can see and interact with directly represents only a tiny portion of reality. This discovery raises profound questions. If most of the universe is invisible, what exactly is it made of? How does it behave? And why does it exist in the first place? These questions push the boundaries of modern science and challenge our understanding of physics at the most fundamental level. As research continues, scientists around the world are developing new experiments, building more sensitive detectors, and designing advanced telescopes to study the invisible universe. Space missions are being planned to map dark matter more precisely, while particle physics experiments attempt to create or detect it under controlled conditions. Each step brings humanity closer to understanding the hidden structure of reality. Yet, despite all progress, the universe still keeps its deepest secrets locked away. Dark matter remains unseen, and dark energy remains unexplained. Together, they form a cosmic mystery that defines the very fabric of existence. What we know is only the beginning, a small glimpse into a vast and invisible universe that surrounds us at every moment. This is where the journey begins, with the recognition that the universe is far stranger than it first appears. What we see is only a fraction of what exists, and behind the visible cosmos lies an unseen structure shaping everything from the smallest galaxy to the largest cosmic web. The search to understand this hidden universe has only just begun, and each discovery leads to even deeper questions about the nature of reality itself. The idea of dark matter did not appear out of nowhere as a sudden invention. It emerged gradually from repeated observations that did not fit with existing scientific understanding. To understand what dark matter might be, it is important to first understand what scientists expected to see in the universe and why those expectations failed. For most of human history, gravity was thought to be a force that could be fully explained by visible matter. Stars, planets, gas, and dust were assumed to be the only ingredients needed to account for how galaxies form and move. But as telescopes became more powerful and measurements became more precise, the universe began to show behavior that could not be explained by anything visible. One of the earliest and most important clues came from studying the rotation of galaxies. A galaxy is a massive system containing billions of stars bound together by gravity. These stars orbit around a central region, much like planets orbit a star. According to Newtonian physics, the speed of orbiting objects depends on how much mass is inside their orbit. In a solar system, planets closer to the Sun move faster because they feel a stronger gravitational pull, while planets farther away move more slowly. This same principle was expected to apply to galaxies. Scientists predicted that stars near the center of a galaxy would move quickly, while stars near the outer edges would move more slowly. However, when astronomers began measuring the actual rotation speeds of galaxies, they found something very different. Instead of slowing down at the edges, stars in the outer regions were moving at nearly the same speed as those closer to the center. This was completely unexpected. It suggested that there was much more mass in galaxies than could be seen. If only visible matter existed, the outer stars should not have enough gravitational force holding them in orbit. They should either move slower or escape entirely. This observation led to a major question. If the visible matter is not enough to explain the motion of stars, then where is the missing mass? The first possibility considered was that the measurements were incorrect or incomplete, but repeated studies of different galaxies confirmed the same pattern. Spiral galaxies, elliptical galaxies, and irregular galaxies all showed similar behavior. The problem was not with a single observation, but with the fundamental understanding of gravity on cosmic scales. To explain this missing mass, scientists introduced the concept of an invisible form of matter. This matter does not emit, absorb, or reflect light, which makes it completely invisible to telescopes. However, it still has mass and therefore produces gravitational effects. This unknown substance was named dark matter. The word dark does not mean it is black or shadowy in appearance. Instead, it means it cannot be detected through electromagnetic radiation, which includes visible light. Once the idea of dark matter was introduced, scientists began searching for more evidence. One of the strongest sources of evidence came from galaxy clusters. These clusters are the largest gravitationally bound structures in the universe, containing hundreds or thousands of galaxies held together by their mutual gravity. When astronomers measured the mass of these clusters based on visible matter alone, they found a serious problem. The galaxies were moving so fast that the clusters should have broken apart long ago. The visible matter was not enough to keep them together. To solve this problem, scientists calculated how much additional mass would be needed to hold the clusters together. The result was surprising. There had to be several times more mass in the cluster than what was visible. This unseen mass was distributed throughout the cluster, not just in individual galaxies, but also in the space between them. This provided strong support for the existence of dark matter on a much larger scale than individual galaxies. Another major breakthrough came from the study of gravitational lensing. This phenomenon occurs when a massive object bends the path of light passing near it. According to Einstein's theory of general relativity, gravity is not just a force, but a curvature of space and time. When light travels near a massive object, its path is curved, causing distant objects to appear distorted, or magnified. By carefully studying how light from distant galaxies is bent as it passes through galaxy clusters, scientists can map the distribution of mass in the universe. This method does not rely on visible light from the mass itself, only on its gravitational effect. When these maps were created, they revealed something unexpected. The regions where light was most strongly bent did not match the distribution of visible matter. Instead, there were large regions of invisible mass surrounding and extending beyond galaxies. This was one of the most important pieces of evidence for dark matter. It showed that whatever this substance is, it is not just an isolated feature of galaxies, but a fundamental component of cosmic structure. It forms vast halos around galaxies and helps shape the large-scale structure of the universe. As evidence accumulated, scientists began to consider what dark matter could actually be made of. Ordinary matter, also known as baryonic matter, is composed of atoms made from protons, neutrons, and electrons. This is the matter that makes up stars, planets, and living organisms. However, dark matter does not behave like ordinary matter. It does not interact with light, and it does not seem to form atoms or molecules. This means it must be something entirely different. One of the leading candidates for dark matter is a class of particles called WIMPs, or weakly interacting massive particles. These hypothetical particles would have mass, meaning they can exert gravitational force, but they would interact with normal matter only through the weak nuclear force and gravity. This would make them extremely difficult to detect because they would pass through ordinary matter almost without any interaction. Another candidate is the axion, a very light and weakly interacting particle originally proposed to solve problems in particle physics. Axions could exist in enormous numbers, filling space and contributing to the overall mass of the universe without being directly visible. There are also sterile neutrinos, a hypothetical type of neutrino that interacts even more weakly than known neutrinos. Despite these theories, no dark matter particle has ever been directly detected. This is one of the most frustrating and exciting challenges in modern physics. Scientists have built highly sensitive detectors deep underground to shield them from cosmic radiation, hoping to catch rare interactions between dark matter particles and ordinary matter. So far, these experiments have produced no confirmed results. Particle accelerators have also been used to search for dark matter. By smashing particles together at extremely high energies, scientists hope to create conditions where dark matter particles might be produced. The Large Hadron Collider has searched for signs of missing energy that could indicate dark matter creation, but no definitive evidence has been found yet. The lack of direct detection does not weaken the case for dark matter. Instead, it shows how mysterious it truly is. The gravitational evidence for dark matter is overwhelming, but its particle nature remains unknown. This makes it one of the most important unsolved problems in physics. Dark matter is not evenly distributed throughout the universe. It forms a cosmic web, a large-scale structure made of filaments and nodes. Galaxies are not randomly scattered through space. Instead, they are found along these filaments, where dark matter is most concentrated. The spaces between filaments are vast cosmic voids with very little matter. This structure suggests that dark matter played a crucial role in the formation of galaxies. In the early universe, after the Big Bang, matter was not evenly distributed. Small fluctuations in density existed, and dark matter helped amplify these fluctuations through gravity. Over time, regions with slightly more dark matter attracted more matter, eventually forming galaxies and clusters. Without dark matter, galaxies might not have formed at all, or they would look very different from what we see today. Computer simulations of the universe support this idea. When dark matter is included in simulations, the resulting structure closely matches the observed distribution of galaxies. Without dark matter, the simulations fail to produce the complex web-like structure of the universe. This provides strong theoretical support for its existence. Despite all this evidence, dark matter remains invisible and undetected in a direct sense. It challenges the very foundation of how science understands the universe. Normally, scientific theories are confirmed through direct observation or experimentation. But dark matter exists in a different category. It is known through its effects rather than its direct presence. This raises an important question about the nature of scientific knowledge. If something cannot be seen or directly measured, but its effects are clearly observed, does it still count as real? In the case of dark matter, the scientific community has largely agreed that the evidence is too strong to ignore. The gravitational effects are consistent, repeatable, and observed across many independent systems. However, the mystery remains incomplete. Scientists still do not know what dark matter is, where it comes from, or how it fits into the broader framework of physics. It may require new physics beyond the standard model of particle physics, which currently describes all known fundamental particles and forces except gravity. The search for dark matter continues across multiple fields of science. Astronomers study galaxies and cosmic structures, physicists conduct underground experiments, and cosmologists simulate the evolution of the universe. Each approach adds a piece to the puzzle, but the full picture is still missing. What makes dark matter especially fascinating is that it is not just a minor detail in the universe, it is one of its main components. Ordinary matter, the kind that makes up everything we see, accounts for only a small fraction of the total mass of the universe. Dark matter makes up a much larger portion, shaping the gravitational framework of everything from galaxies to clusters. This means that most of the universe is invisible and unknown. Every galaxy, including our own Milky Way, is embedded in a massive halo of dark matter. We live inside a structure that is shaped by something we cannot see or directly interact with. This realization changes how we think about reality itself. The journey to understand dark matter is still ongoing. Each new discovery brings more questions than answers. But this is what makes it one of the most important areas of modern science. It forces us to confront the limits of our knowledge and push beyond them. The universe is not just what we see, it is also what we cannot see, and dark matter is the key to understanding that hidden side of reality. When scientists first realized that galaxies were not behaving as expected, the problem seemed isolated. It looked like a mismatch in how stars moved within individual galaxies. But as observations improved and telescopes became more advanced, a much larger pattern began to emerge. The strange behavior of galaxies was not random, it was consistent across the universe. This consistency suggested that something fundamental was missing from our understanding of cosmic structure. To uncover this missing piece, astronomers began to study galaxies in greater detail, focusing not just on their motion, but on how they were distributed, how they interacted, and how they evolved over time. One of the most important discoveries came from studying the rotation curves of spiral galaxies. These curves show how fast stars orbit the center of a galaxy at different distances. If only visible matter were present, the curve should rise sharply near the center and then fall as distance increases. This is because most visible mass is concentrated in the central region. But instead of falling, the curves remained flat. This meant that stars far from the center were moving much faster than they should based on visible matter alone. This observation was repeated in many galaxies, including our own Milky Way. The Milky Way is a spiral galaxy containing hundreds of billions of stars. When scientists measured the motion of stars and gas clouds within it, they found the same pattern. The outer regions were rotating too quickly. This could only be explained if there was a large amount of unseen mass extending far beyond the visible edge of the galaxy. This unseen mass formed what is now known as a dark matter halo. The idea of a halo was important because it changed how scientists thought about galaxies. Instead of being isolated structures made mostly of stars and gas, galaxies were now seen as embedded within much larger, invisible structures. These halos were not small or insignificant. They contained most of the mass of the galaxy system. The visible part of a galaxy, the stars and glowing gas, was just a small central region within a much larger dark structure. As astronomers studied more galaxies, they noticed that the size of these halos varied depending on the galaxy's mass. Larger galaxies had larger halos, while smaller galaxies had smaller ones. This suggested that dark matter was not randomly distributed, but followed a consistent pattern throughout the universe. It was somehow linked to the formation and evolution of galaxies. To understand this relationship, scientists began looking back in time by observing distant galaxies. Because light takes time to travel, looking deeper into space means looking further back in time. When astronomers observed galaxies billions of light years away, they were seeing them as they were in the early universe. These young galaxies were less structured, but still showed signs of dark matter influence. Even in the early universe, matter was not evenly distributed. There were small fluctuations in density, tiny regions where matter was slightly more concentrated. Over time, gravity amplified these differences. Regions with more matter attracted even more matter, gradually forming the large structures we see today. Dark matter played a crucial role in this process. Because it interacts through gravity, but not through light or radiation, it began clumping together earlier than normal matter. This created gravitational wells into which normal matter later fell. Without dark matter, the formation of galaxies would have been much slower and less efficient. In fact, many simulations show that without dark matter, the universe would remain mostly uniform, without the rich structure of galaxies, clusters, and filaments. This means that dark matter is not just a mysterious component of the universe. It is a foundational element in the creation of cosmic structure. As this idea developed, scientists began to think of dark matter as the scaffolding of the universe. It forms the invisible framework upon which visible matter builds. Galaxies form along the densest regions of this scaffolding, like cities forming along highways. This metaphor helped explain why galaxies are not randomly scattered, but instead form complex networks across space. These networks are known as the cosmic web. The cosmic web is one of the most striking, large-scale structures in the universe. It consists of long filaments of matter stretching across millions of light years, connecting dense clusters of galaxies. Between these filaments are vast empty regions known as voids, where very little matter exists. The structure resembles a three-dimensional web, with dark matter forming the threads and galaxies forming the nodes. Computer simulations played a key role in discovering the cosmic web. By modeling the universe from its early stages, scientists were able to see how small fluctuations in density evolved over billions of years. When dark matter was included in these simulations, the result closely matched the observed universe. Filaments formed naturally as gravity pulled matter together along preferred paths. Without dark matter, the simulations failed to produce this structure. Observational evidence for the cosmic web also comes from mapping galaxy distributions. Large sky surveys have catalogued millions of galaxies, revealing their positions in space. When these positions are plotted, they clearly show filamentary structures and voids. This pattern confirms that galaxies are not isolated objects, but part of a much larger interconnected system shaped by gravity and dark matter. One of the most powerful tools for studying dark matter in this context is gravitational lensing. As discussed earlier, massive objects bend light. But on cosmic scales, this effect becomes even more important. Entire clusters of galaxies can act as lenses, distorting and magnifying the light from galaxies behind them. By analyzing these distortions, scientists can reconstruct the distribution of both visible and invisible matter. Gravitational lensing has revealed that dark matter is not evenly smooth. Instead, it is clumpy, forming dense regions within halos and filaments. These clumps help guide the formation of galaxies by acting as gravitational seeds. Where dark matter is more concentrated, galaxies are more likely to form. Where it is less concentrated, fewer galaxies appear. Another important discovery came from studying the bullet cluster, one of the most famous pieces of evidence for dark matter. The bullet cluster is actually two galaxy clusters that have collided. During the collision, the hot gas within the clusters interacted and slowed down, while the galaxies passed through each other with minimal interaction. However, when scientists mapped the mass distribution using gravitational lensing, they found that most of the mass was not located where the visible gas was. Instead, it was located in regions corresponding to the galaxies, suggesting that most of the mass is in a collisionless form, consistent with dark matter. This observation is extremely important because it separates visible matter from the majority of mass in a clear and direct way. It shows that dark matter does not behave like ordinary matter during collisions. It passes through other matter without interacting, except through gravity. This is one of the strongest pieces of evidence that dark matter is a unique form of matter and not simply hidden ordinary matter like faint stars or gas clouds. As the study of dark matter progressed, scientists began to understand its role, not just in structure formation, but also in the stability of galaxies. Without dark matter halos, galaxies would not be able to hold their shape. The outer stars would drift away, and spiral structures would be unstable. Dark matter acts like a gravitational anchor, holding galaxies together over billions of years. This stability also affects how galaxies interact with each other. When galaxies pass near each other, their dark matter halos interact first. This interaction can slow them down or alter their paths, even before the visible parts of the galaxies come into contact. In some cases, galaxies merge, forming larger structures. These mergers are guided largely by the gravitational influence of dark matter. The influence of dark matter extends beyond individual galaxies and clusters. It affects the entire expansion history of the universe. While dark energy drives the acceleration of expansion, dark matter slows down local gravitational collapse and helps shape where structures form. The balance between these components determines the large-scale appearance of the cosmos. Despite its importance, dark matter remains invisible and undetected in laboratories. This creates a deep tension in physics. On one hand, its gravitational effects are undeniable and observed across the universe. On the other hand, no experiment has yet captured a dark matter particle directly. This gap between theory and observation is one of the central challenges in modern science. Some scientists have proposed that dark matter might not be made of particles at all. Instead, it could be a manifestation of modified gravity. In this idea, gravity behaves differently at large scales than currently understood. This would remove the need for dark matter entirely. However, most evidence still supports the existence of a physical substance rather than a modification of gravity. The reason dark matter is so difficult to detect is that it interacts extremely weakly with normal matter. It does not emit light, absorb light, or scatter light. It passes through detectors almost unnoticed. Even though trillions of dark matter particles may pass through your body every second, they leave no trace. This leads to a strange reality. We are surrounded by something that makes up most of the universe, yet we cannot feel it, see it, or directly measure it. We only know it exists because of its gravitational influence on everything we can observe. The study of galaxy formation, structure, and motion continues to provide strong evidence for dark matter. Every new observation adds more support to the idea that the universe is built on an invisible foundation. This foundation shapes everything from the smallest galaxies to the largest cosmic structures. As research continues, scientists are developing more advanced tools to map dark matter in greater detail. New telescopes, more sensitive detectors, and larger simulations are being used to explore its properties. Each discovery brings us closer to understanding the invisible framework of the universe. But for now, dark matter remains one of the deepest mysteries in science. It is everywhere, yet unseen. It shapes galaxies, yet cannot be touched. It holds the universe together, yet its true nature is still unknown. As astronomers gathered more evidence that something invisible was shaping the universe, a deeper question began to emerge. It was no longer just about missing mass in galaxies. It was about the nature of gravity itself. If visible matter could not explain the motion of galaxies, then either there was unseen matter providing extra gravity, or our understanding of gravity was incomplete. This question opened one of the most important debates in modern physics, a debate that still continues today. Galaxy clusters, for example, contain far more gravitational mass than can be explained by visible matter alone. MOND can partially account for some of this discrepancy, but not all of it. In addition, observations of gravitational lensing, where light is bent by massive objects, often show mass distributions that cannot be fully explained by modified gravity alone. These inconsistencies have made it difficult for MOND to replace dark matter as a complete theory. Another major challenge for modified gravity theories comes from the cosmic microwave background, often called the CMB. The CMB is the afterglow of the Big Bang, a faint radiation that fills the entire universe. It provides a snapshot of the early universe, when matter was still very evenly distributed. Tiny fluctuations in the CMB represent the seeds of future galaxies and cosmic structures. When scientists analyze these fluctuations, they find patterns that strongly support the existence of dark matter. The structure of the CMB matches predictions from models that include dark matter, but it does not fit well with most modified gravity theories. This is one of the strongest pieces of evidence in favor of dark matter over modified gravity. Despite these challenges, the idea of modifying gravity remains an active area of research. This is because the nature of gravity is still not fully understood at a fundamental level. While general relativity describes gravity extremely well on large scales, it does not yet unify with quantum mechanics, which describes the behavior of particles at the smallest scales. This lack of a unified theory leaves room for new ideas and possibilities. Ordinary matter interacts strongly with electromagnetic radiation, which is why we can see it. It emits or reflects light, allowing telescopes to detect it across vast distances. Dark matter, on the other hand, does not interact with light at all. It does not absorb, reflect, or emit electromagnetic radiation. This is why it is invisible. But invisibility alone is not enough. The particle must also have mass and must not interact strongly with itself or with ordinary matter. Otherwise it would behave differently in galaxies and clusters than what is observed. This combination of properties has led scientists to propose that dark matter is made of entirely new types of particles that have not yet been detected. These particles would exist beyond the standard model, representing new physics waiting to be discovered. One of the most widely studied candidates is the weakly interacting massive particle, commonly known as WIMP. The name describes its properties. WIMPs are expected to have mass, meaning they contribute to gravity, but they interact only through the weak nuclear force and gravity. This makes them extremely difficult to detect because the weak force operates only at very short distances and is much less noticeable than electromagnetism. WIMPs became popular because they naturally arise in several extensions of the standard model, including supersymmetry. Supersymmetry is a theoretical framework that proposes every known particle has a heavier partner particle. In many versions of this theory, the lightest supersymmetric particle is stable and has the right properties to be dark matter. If such particles were created in the early universe, they could still exist today, filling galaxies and cosmic halos. To detect WIMPs, scientists have built extremely sensitive experiments deep underground. These detectors are placed beneath layers of rock to shield them from cosmic rays and other background radiation. The goal is to observe rare collisions between dark matter particles and atomic nuclei. If a WIMP passes through the detector and interacts with the nucleus, it would produce a tiny flash of energy or a small recoil that could be measured. Despite decades of searching, no definitive detection of WIMPs has been made. Experiments such as xenon-based detectors and cryogenic crystal detectors have pushed the limits of sensitivity further and further, but the expected signals remain absent. This does not completely rule out WIMPs, but it does place strong constraints on their possible properties. If they exist, they must interact even more weakly than originally thought, or have masses outside the most expected range. Another important candidate for dark matter is the axion. Unlike WIMPs, axions are extremely light particles. They were originally proposed to solve a completely different problem in particle physics related to the strong nuclear force and symmetry violations. However, physicists later realized that axions could also serve as dark matter. Axions would behave very differently from WIMPs. Instead of being heavy and sparse, they would be extremely light and abundant. In some models, axions could form a kind of cosmic field that fills space. This field would oscillate very slowly, contributing to the overall mass of the universe without interacting strongly with normal matter. Detecting axions is even more challenging than detecting WIMPs. Because they interact so weakly, they require highly specialized experiments that use strong magnetic fields to convert axions into detectable photons. These experiments are still ongoing, and while no confirmed detection has been made, they continue to explore new regions of possible axion properties. Another candidate comes from neutrinos, specifically a hypothetical type called sterile neutrinos. Ordinary neutrinos are already known to be extremely weakly interacting particles with very small mass. They can pass through entire planets without being stopped. However, they are still not suitable as the main component of dark matter, because their properties do not match cosmological observations. Sterile neutrinos would be even more elusive. They would not interact through the weak nuclear force at all, only through gravity and possibly mixing with ordinary neutrinos. If they exist, they could form dark matter in certain regions of the universe. Some observations in X-ray astronomy have hinted at possible signals that might be related to sterile neutrinos, but these results remain uncertain and controversial. Beyond these particle-based ideas, there are also more exotic theories. Some scientists propose that dark matter might be composed of primordial black holes. These are black holes formed in the early universe, not from collapsing stars, but from extreme density fluctuations shortly after the Big Bang. If enough of these small black holes exist, they could collectively account for dark matter. However, observations have placed strong limits on how many primordial black holes could exist. If they were too abundant, they would have been detected through gravitational lensing or other astrophysical effects. While they may still contribute a small fraction of dark matter, they are unlikely to make up all of it. Another exotic idea involves hidden sectors of physics. In this scenario, dark matter is not just one type of particle, but part of an entirely separate set of particles and forces that do not interact with ordinary matter except through gravity. This hidden sector could be as complex as the visible universe, with its own structure, interactions, and possibly even forms of dark stars or dark galaxies. If such a hidden sector exists, it would mean that the universe is far richer and more complex than previously imagined. We would only be seeing one side of a much larger cosmic reality. Despite the variety of theories, all dark matter candidates must satisfy the same basic requirements. They must have mass to explain gravitational effects, they must interact very weakly with light to remain invisible, and they must be stable enough to still exist today, billions of years after the formation of the universe. These constraints make the problem extremely difficult. Many particles that are proposed theoretically fail to meet all these conditions. This is why dark matter remains one of the most important unsolved problems in physics. The search for dark matter is not limited to underground detectors. Particle accelerators also play a key role. The Large Hadron Collider, the most powerful particle accelerator in the world, smashes protons together at extremely high energies. These collisions recreate conditions similar to those just after the Big Bang. If dark matter particles can be produced in such collisions, they might be detected indirectly through missing energy. In a particle collision, the total energy and momentum before and after the event must be conserved. If some energy appears to be missing, it could indicate the production of invisible particles that escaped detection. So far, no clear missing energy signal has been linked to dark matter, but the search continues. Cosmology also provides important constraints on dark matter candidates. Observations of the cosmic microwave background, galaxy formation, and large-scale structure all provide information about how dark matter behaves. Any viable particle must fit within this cosmological framework. This makes the problem not just one of particle physics, but of the entire universe. One of the most important insights from cosmology is that dark matter must be cold. In this context, cold does not mean temperature in the everyday sense, but rather that the particles move slowly compared to the speed of light. Cold dark matter allows structures to form efficiently in the early universe. If dark matter were too fast or energetic, it would smooth out density fluctuations and prevent galaxies from forming as we see them today. This idea led to the widely accepted model known as lambda cold dark matter, or LCDM. In this model, the universe consists of ordinary matter, cold dark matter, and dark energy. This framework successfully explains most large-scale observations, including galaxy distribution and cosmic microwave background patterns. However, even LCDM is not perfect. On smaller scales, such as within individual galaxies, there are still some discrepancies between predictions and observations. These tensions have led some scientists to consider whether dark matter might have more complex properties than simple cold collisionless particles. For example, some models propose self-interacting dark matter, where dark matter particles can collide with each other through forces other than gravity. This could help explain certain galactic structures and density profiles that do not match simple models. Other ideas suggest fuzzy dark matter, where ultralight particles behave more like waves than particles. In this case, dark matter would have wave-like properties on galactic scales, smoothing out structures in specific ways. Each of these models attempts to solve specific problems while staying consistent with the overall evidence for dark matter. But none has yet emerged as the definitive explanation. The search for dark matter particles is one of the most active areas of modern science. It involves collaboration between astrophysicists, particle physicists, and cosmologists. Each field provides different pieces of the puzzle, from cosmic structure to laboratory experiments. What makes this search so unique is that it connects the very large with the very small. Dark matter influences galaxies that span millions of light years, yet its nature may depend on particles smaller than atoms. It is a bridge between cosmology and quantum physics. As experiments become more sensitive and observations more precise, the range of possible dark matter candidates continues to shrink. Each null result eliminates one possibility and pushes scientists toward new ideas. But the mystery remains unsolved. Dark matter continues to reveal itself only through gravity, never through direct interaction. It shapes the universe silently, invisibly, and consistently. The question of what dark matter is made of is still open. It may be a new particle, a new field, or something even more fundamental that we have not yet imagined. Whatever the answer turns out to be, it will likely transform our understanding of physics at the deepest level. For now, dark matter remains one of the greatest unknowns in science. It is a hidden substance that fills the universe, binds galaxies together, and shapes cosmic history. Yet it has never been seen directly. The search for its true nature continues, driven by the hope that one day the invisible will finally become known. For much of human history, the universe was thought to be static and unchanging on the largest scales. Ancient astronomers observed the stars and saw patterns that seemed eternal. Even when galaxies were later discovered, they were assumed to be stable systems moving through a fixed cosmic background. Space itself was considered a passive stage where objects moved, but the stage did not change. This view of the universe began to collapse in the early 20th century when new observations revealed that space itself is dynamic. The universe is expanding, and this expansion is not slowing down under gravity as expected. Instead, it is accelerating. This discovery led to one of the most surprising and mysterious concepts in modern cosmology, a force or property of space known as dark energy. The story begins with the expansion of the universe. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery. By observing distant galaxies, he found that almost all of them were moving away from us. More importantly, the farther away a galaxy was, the faster it appeared to be receding. This relationship became known as Hubble's law. It provided clear evidence that the universe is not static, but expanding in all directions. Space itself is stretching, carrying galaxies along with it. At first, this expansion was thought to be slowing down due to the gravitational attraction of all matter in the universe. Just like a thrown ball slows down due to gravity, it was expected that the expansion of the universe would gradually decelerate over time. For decades, cosmologists worked under this assumption. The main question was not whether the universe would slow down, but how quickly it would do so. However, in the late 1990s, this expectation was overturned by one of the most unexpected discoveries in cosmology. Two independent teams of astronomers were studying distant supernovae, specifically a type known as Type Ia supernovae. These supernovae are extremely useful in astronomy because they have a consistent intrinsic brightness, allowing scientists to measure distances across the universe with high precision. By comparing the brightness of these supernovae with their redshift, which indicates how fast they are moving away from us, scientists can determine how the expansion rate of the universe has changed over time. The expectation was that distant supernovae would appear slightly brighter than predicted by a decelerating universe model, because the expansion should have slowed down in the past. Instead, the opposite was observed. The supernovae appeared dimmer than expected, meaning they were farther away than they should have been in a slowing universe. This surprising result led to a shocking conclusion. The expansion of the universe is not slowing down, it is accelerating. This meant that something was acting against gravity on the largest scales, pushing galaxies apart at an increasing rate. This unknown cause was given the name dark energy. Dark energy is not a form of matter like dark matter. Instead, it appears to be a property of space itself. It is evenly distributed throughout the universe and does not clump together like matter. Unlike dark matter, which pulls objects together through gravity, dark energy seems to push space apart. It affects the expansion of the universe rather than the motion of objects within galaxies. One of the simplest ways to understand dark energy is to think of space as having an internal pressure. As the universe expands, more space is created, and this space itself carries energy. This energy does not dilute as the universe grows, unlike matter or radiation. Instead, it remains constant or even increases as space expands. This leads to a runaway effect, where expansion accelerates over time. The concept of dark energy is closely related to Einstein's theory of general relativity. When Einstein first developed his equations, he believed the universe was static. To make his equations match this belief, he introduced a term called the cosmological constant. This constant acted as a repulsive force that could balance gravity and keep the universe from collapsing or expanding. Later, after Hubble's discovery of expansion, Einstein reportedly called this his greatest mistake because the need for the cosmological constant seemed to disappear. However, the discovery of accelerated expansion brought the cosmological constant back into focus. It turns out that a term very similar to Einstein's original idea may actually be responsible for dark energy. In modern cosmology, the cosmological constant is one of the leading explanations for dark energy. It represents a constant energy density filling space uniformly. Despite its mathematical simplicity, the physical origin of this energy is deeply mysterious. According to quantum field theory, empty space is not truly empty. It is filled with virtual particles that constantly appear and disappear due to quantum fluctuations. These fluctuations contribute a small amount of energy to space. However, when physicists attempt to calculate this vacuum energy, the result is enormously larger than what is observed from cosmic acceleration. The difference between theoretical predictions and observations is one of the biggest unsolved problems in physics. This discrepancy suggests that either our understanding of quantum physics is incomplete, or there is a mechanism that cancels most of the vacuum energy, leaving only a tiny residual effect that we observe as dark energy. Understanding this mechanism is one of the greatest challenges in theoretical physics today. To measure dark energy more precisely, scientists study the expansion history of the universe using multiple methods. One of the most important methods involves observing distant galaxies and supernovae at different stages of cosmic history. By mapping how the expansion rate changes over time, scientists can reconstruct the influence of dark energy throughout the evolution of the universe. Another important method is studying the cosmic microwave background. This radiation comes from the early universe, just 380,000 years after the Big Bang. Tiny fluctuations in the temperature of this radiation contain information about the composition of the universe. By analyzing these fluctuations, scientists can determine how much dark energy, dark matter, and ordinary matter exist in the cosmos. These observations reveal a striking result. Dark energy makes up about 70% of the total energy content of the universe. Dark matter accounts for about 25%, and ordinary matter makes up only about 5%. This means that everything we can see, stars, planets, galaxies, and even ourselves, represents only a tiny fraction of the universe. The dominance of dark energy raises profound questions. If it is so abundant, why did it only begin to dominate recently in cosmic history? In the early universe, matter was much denser, and its gravitational attraction slowed the expansion of space. Over time, as the universe expanded and matter became more diluted, dark energy began to dominate. This transition marked a major shift in the evolution of the cosmos. Before dark energy became dominant, the universe's expansion was slowing down due to gravity. Galaxies were forming, clusters were growing, and structures were becoming more complex. But as dark energy took over, the expansion began to accelerate, pulling galaxies apart faster and faster. This means that in the distant future, galaxies outside our local group will eventually move away so quickly that they will no longer be observable. This leads to a dramatic vision of the far future universe. In billions of years, galaxies beyond our local group will disappear from view as space expands faster than light can travel across it. The universe will become darker and more isolated. Only gravitationally bound systems, such as our local galaxy group, will remain visible. There are several competing theories about the nature of dark energy. The simplest is the cosmological constant, which assumes that dark energy has a constant density throughout space and time. This model fits current observations very well, and is part of the standard cosmological model known as lambda cold dark matter. However, some scientists propose that dark energy may not be constant. Instead, it could be dynamic, changing over time. These models are called quintessence models. In these theories, dark energy is caused by a field that evolves slowly across the universe. This field could change strength over billions of years, leading to different expansion behaviors in the past and future. Other theories suggest that dark energy might be related to modifications of gravity on very large scales. In this view, the accelerated expansion of the universe is not caused by a new form of energy, but by a breakdown of general relativity at cosmological distances. If gravity behaves differently across vast stretches of space, it could produce effects similar to dark energy. There are also more speculative ideas involving extra dimensions. In some theories, inspired by string theory, our universe may exist on a three-dimensional surface within a higher dimensional space. Dark energy could arise from interactions between our universe and these extra dimensions, causing the observed acceleration. Despite these many ideas, no single theory has yet been proven. Dark energy remains one of the deepest mysteries in physics. Unlike dark matter, which affects the structure of galaxies and can be indirectly mapped, dark energy is smooth and uniform, making it even harder to study. It does not cluster or form structures. It simply exists everywhere, influencing the expansion of space itself. One of the most important challenges in understanding dark energy is measuring whether it changes over time. Future telescopes and space missions are being designed to map the expansion history of the universe with extreme precision. By studying billions of galaxies and supernovae, scientists hope to determine whether dark energy is truly constant or evolving. Another approach involves studying the growth of cosmic structures. Dark energy affects how fast galaxies and clusters form. By comparing observations with theoretical models, scientists can test different explanations of its nature. Even small deviations from predictions could provide clues about what dark energy really is. The discovery of dark energy has completely changed our understanding of the universe. It revealed that space is not just an empty backdrop, but an active component of reality with its own properties. It also showed that the ultimate fate of the universe depends not just on matter and gravity, but on this mysterious force that dominates cosmic expansion. Before dark energy was discovered, the question of the universe's fate seemed straightforward. It was thought that gravity would eventually slow expansion, possibly leading to a collapse or a slow coasting expansion. Now, the picture is very different. The universe is not slowing down. It is accelerating toward an ever more empty and isolated state. Dark energy is not just a scientific concept. It is a fundamental part of the universe that shapes its destiny. It determines how galaxies move, how space evolves, and how the cosmos will end. Yet its true nature remains unknown. The more we study the universe, the more we realize that most of it is invisible and unexplained. Dark matter holds galaxies together. Dark energy pushes them apart. Between them, they control the structure and fate of everything we see, and yet both remain mysterious. The journey to understand dark energy is still in its early stages. Each new observation brings us closer to understanding the expansion of the universe, but also reveals new questions. The universe is not just expanding, it is evolving in ways that challenge our deepest understanding of physics. In the end, dark energy reminds us that the universe is far stranger than it appears. Space itself is not empty. It is alive, with a hidden energy that shapes everything on the largest scales. And the story of this invisible force is still being written. The discovery that the universe is expanding did not happen in a single moment. It was the result of many small steps, each building on the work of earlier scientists who were trying to understand the structure of space itself. For most of human history, the universe was thought to be static and unchanging on the largest scales. Stars were seen as fixed points in the sky, and the idea that the cosmos itself could evolve or grow was not part of scientific thinking. Space was considered eternal and unchanging, and time was thought to unfold within it without affecting its structure. This view began to change in the early 20th century, when mathematics and observation started to reveal a very different reality. One of the first major breakthroughs came from theoretical work. A scientist named Alexander Friedmann studied Einstein's equations of general relativity and found something unexpected. While Einstein believed his equations described a static universe, Friedmann showed that the equations actually allowed for a dynamic universe that could expand or contract. His solutions suggested that space itself could change over time, growing or shrinking depending on its energy and matter content. At the time, this idea was not widely accepted because there was no clear observational evidence to support it. But mathematically, the possibility of an expanding universe had been opened. A few years later, another important contribution came from Georges Lemaitre, a Belgian priest and physicist. Lemaitre independently reached similar conclusions to Friedmann. He proposed that the universe began from a very dense state and has been expanding ever since. He described what he called the primeval atom, an early idea that resembles what we now call the Big Bang theory. Lemaitre's work connected theoretical physics with the idea of a cosmic beginning, suggesting that the universe had a history and was not static. Even with these theoretical insights, the idea of an expanding universe still required observational proof. That proof came from astronomy, specifically from the study of distant galaxies. In the early 20th century, astronomers were able to measure the spectra of light coming from galaxies outside the Milky Way. When light is split into its component colors, it produces a pattern of lines that can be used to determine the motion of the object emitting it. If an object is moving away, its light shifts toward the red end of the spectrum. This effect is known as redshift. By measuring the redshift of galaxies, astronomers discovered that almost all galaxies were moving away from us. More importantly, the farther away a galaxy was, the greater its redshift. This meant that more distant galaxies were moving away faster. This relationship was first clearly established by Edwin Hubble, whose observations in the 1920s provided strong evidence that the universe is expanding. Hubble's discovery was revolutionary because it changed the fundamental understanding of the cosmos. Instead of being a static collection of galaxies, the universe was now seen as a dynamic system where space itself is stretching. This meant that galaxies are not moving through space in the traditional sense. Instead, space itself is expanding, carrying galaxies along with it like raisins in a rising loaf of bread. This idea required a major shift in thinking. If space is expanding, then the distances between galaxies are increasing over time. This also means that in the past, galaxies were much closer together. If we go far enough back in time, the universe must have been extremely dense and hot, with all matter concentrated in a small region. This is the foundation of the Big Bang model. At first, the idea of an expanding universe was not universally accepted. Many scientists preferred the idea of a steady-state universe, where the cosmos is eternal and unchanging on the largest scales, with new matter continuously created as space expands. This model avoided the idea of a beginning, which some scientists and philosophers found uncomfortable. However, as more evidence accumulated, the expanding universe model began to gain stronger support. One of the key pieces of evidence came from improved measurements of galaxy distances and redshifts. As technology advanced, astronomers were able to measure more galaxies with greater precision. The linear relationship between distance and redshift became clearer and more reliable. This relationship is now known as Hubble's law, and it forms one of the foundational pillars of modern cosmology. Hubble's law implies that the universe has a measurable expansion rate. This rate is known as the Hubble constant. By determining the value of this constant, scientists can estimate the age of the universe and understand how quickly space is expanding today. However, measuring the Hubble constant precisely has proven to be surprisingly difficult, and different methods sometimes produce slightly different results. This tension remains an active area of research. As the expanding universe model became more widely accepted, scientists began to explore its implications. If the universe is expanding, then it must have been smaller in the past. Tracing this expansion backward leads to a point where the universe was extremely dense and hot. This idea eventually developed into the Big Bang theory, which describes the early evolution of the universe from an initial state of high density and temperature. The Big Bang theory does not describe an explosion in space, but rather an expansion of space itself. It is not that matter exploded into empty space. Instead, space, time, and matter all emerged from a very dense initial state and have been expanding ever since. This distinction is important because it changes how we think about the origin of the universe. One of the strongest pieces of evidence for the Big Bang came much later with the discovery of the cosmic microwave background radiation. This faint radiation fills the entire universe and is considered the afterglow of the early universe when it was hot and dense. Its existence confirmed that the universe had a hot beginning and has been cooling as it expands. While this discovery was covered in other contexts, it fits naturally into the story of the expanding universe because it provides direct evidence of its early state. The expansion of the universe also has profound implications for the future. If the expansion continues, galaxies will move farther apart over time. Eventually, distant galaxies will become unreachable and invisible as their light is stretched beyond detection. The universe will become increasingly isolated, with only local structures remaining visible to observers. However, the rate of expansion is not constant. It depends on the contents of the universe, including dark matter and dark energy. In the early universe, expansion was slowing due to the gravitational pull of matter. Later, as dark energy became dominant, expansion began to accelerate. This changing behavior makes the history of cosmic expansion a complex and dynamic process. Understanding this history requires combining observations with theoretical models. Scientists use Einstein's equations of general relativity to describe how space evolves over time. These equations link the curvature of space to its energy content, including matter, radiation, and dark energy. By solving these equations under different conditions, cosmologists can predict how the universe expands at different stages of its history. These models are then tested against observations of galaxies, supernovae, and the cosmic microwave background. When all the data is combined, the result is a consistent picture of an expanding universe that began in a hot, dense state and has been evolving for billions of years. One of the most fascinating aspects of cosmic expansion is that it is not something happening within space, but rather something happening to space itself. This means that there is no center of expansion. Every point in the universe sees other galaxies moving away, and the farther they are, the faster they appear to recede. From any galaxy, the universe would appear to be expanding in the same way. This concept challenges everyday intuition. On Earth, expansion usually means objects moving through space. But in cosmology, expansion means space itself is stretching. This distinction is crucial for understanding large-scale structure and the evolution of the universe. As the universe expands, wavelengths of light traveling through space are also stretched. This causes the redshift observed in distant galaxies. The more space the light travels through, the more its wavelength is stretched. This is why very distant galaxies appear redshifted. In extreme cases, their light can be stretched beyond the visible spectrum entirely, making them undetectable. The expansion of space also affects the temperature of the universe. As space expands, radiation becomes diluted and cooler. This cooling process is responsible for the current low temperature of the cosmic microwave background, which is only a few degrees above absolute zero. This provides another strong confirmation of the expanding universe model. Despite the success of the expanding universe theory, many questions remain. One of the biggest is what caused the initial expansion in the first place. The Big Bang Theory describes how the universe evolved after it began, but it does not fully explain why it began or what triggered the initial expansion. These questions remain open in cosmology and may require new physics to answer. Another open question is the ultimate fate of the universe. If expansion continues forever, the universe may eventually become cold and empty. If dark energy changes over time, different outcomes are possible, including scenarios where expansion slows or reverses. Understanding dark energy is therefore essential for predicting the long-term future of the cosmos. The discovery of the expanding universe fundamentally changed humanity's view of reality. It revealed that the cosmos is not static but evolving, with a history stretching back billions of years. It showed that space itself is dynamic and that the universe has been changing since its earliest moments. This realization also set the stage for modern cosmology. Once scientists understood that the universe is expanding, they could begin to reconstruct its past and model its future. The expanding universe became the framework within which all other cosmic phenomena, including dark matter and dark energy, could be understood. In the end, the discovery of expansion is not just about galaxies moving away from each other. It is about the nature of space, time, and existence itself. It revealed that the universe is not a fixed structure, but a living, evolving system. And as we continue to study it, we are still uncovering the full story of how it began, how it grows, and how it will eventually change in the distant future. The discovery of the accelerating universe did not come from a single observation alone. It was the result of careful, long-term studies of some of the most powerful events in the cosmos. Among these events, supernovae played a central role. These exploding stars became one of the most important tools in modern cosmology, allowing scientists to measure distances across billions of light years and uncover the hidden behavior of the universe itself. Without supernovae, the discovery of dark energy might not have been possible. A supernova is the explosive death of a star. When certain types of stars reach the end of their life cycles, they undergo a catastrophic collapse followed by an enormous explosion that can briefly outshine an entire galaxy. For a short period of time, a single supernova can release more energy than the Sun will produce in its entire lifetime. This makes them visible across vast cosmic distances, even billions of light years away. Among all types of supernovae, one class is especially important for cosmology. These are known as Type Ia supernovae. They occur in binary star systems where a white dwarf star, the dense remnant of a dead star, accumulates matter from a companion star. When the white dwarf reaches a critical mass, it undergoes a runaway nuclear reaction and explodes. What makes Type Ia supernovae so valuable is that they have a relatively consistent intrinsic brightness. This allows them to be used as standard candles for measuring cosmic distances. The idea of a standard candle is simple but powerful. If you know how bright an object truly is, and you measure how bright it appears from Earth, you can calculate how far away it must be. The farther away an object is, the dimmer it appears. By using Type Ia supernovae as standard candles, astronomers can map the expansion of the universe over time with high precision. In the 1990s, two independent teams of astronomers began using this method to study distant supernovae. The goal was to measure how the expansion rate of the universe had changed over billions of years. The expectation was based on well-established physics. Gravity should be slowing the expansion of the universe. This means that in the past, the expansion rate should have been faster and more recent expansion should be slower. Distant supernovae, which are seen as they were in the past, should appear slightly brighter than predicted by a decelerating universe model. However, when the data was collected and analyzed, the results were not what anyone expected. The distant supernovae were dimmer than they should have been. This meant they were farther away than predicted. The only way to explain this was that the expansion of the universe was not slowing down. It was accelerating. This discovery was shocking. It contradicted decades of assumptions about cosmology. Gravity, the force that pulls everything together, was expected to dominate the large-scale behavior of the universe. Instead, something was pushing galaxies apart faster and faster. This unknown influence became known as dark energy. The supernova observations were so unexpected that scientists initially questioned whether there were errors in the data. Could the supernovae be different in the past? Could dust or other cosmic effects be dimming their light? Both research teams carefully checked their results, accounting for every possible source of error. After extensive analysis, the conclusion remained the same. The universe is accelerating. This discovery marked one of the most important breakthroughs in modern science. It showed that the universe is not only expanding, but doing so at an increasing rate. The implications were profound, suggesting that most of the energy content of the universe is made of something completely unknown. To understand why supernovae are so powerful as tools for cosmology, it is important to look more closely at how they work. A type Ia supernova has a very specific mechanism. In a binary system, a white dwarf star gradually pulls material from its companion star. As this material accumulates, the white dwarf becomes more massive. However, there is a limit to how massive a white dwarf can become before it becomes unstable. This limit is known as the Chandrasekhar limit. Once this limit is reached, the pressure and temperature inside the white dwarf becomes so extreme that carbon fusion ignites throughout the star almost simultaneously. Unlike normal stellar fusion, which happens in a controlled manner, this reaction is explosive and uncontrollable. The entire star is destroyed in a matter of seconds, releasing an enormous amount of energy. Because this process occurs in a very consistent way, type Ia supernovae tend to have similar peak brightness. This consistency makes them extremely useful for measuring distances. By comparing their known intrinsic brightness with their observed brightness, astronomers can determine how far away they are. Using this method, scientists can build a map of the universe at different points in time. Each supernova acts like a marker, showing how far space has expanded since the light was emitted. By studying many supernovae at different distances, it is possible to reconstruct the expansion history of the universe. When this technique was applied in the 1990s, it led directly to the discovery of cosmic acceleration. The results showed that the expansion rate of the universe was not constant or slowing down. Instead, it had begun to speed up several billion years ago. This finding raised a fundamental question. What could cause the expansion of the universe to accelerate? According to known physics, gravity should be the dominant force on large scales. Gravity pulls matter together, not apart. For expansion to accelerate, there must be some form of energy that counteracts gravity and becomes stronger as space expands. This unknown energy was named dark energy. Unlike matter or radiation, dark energy does not dilute as the universe expands. Instead, its density remains constant or even increases, meaning that as space grows, more dark energy appears to be present. This leads to a feedback effect where expansion accelerates over time. One of the most important implications of this discovery is that dark energy dominates the universe. It is not a minor component, but the largest one. Observations suggest that around 70% of the universe is made of dark energy, while dark matter makes up about 25%, and ordinary matter only about 5%. This means that the vast majority of the universe is composed of something completely unknown. Everything we see, stars, galaxies, planets, and even human beings, is made of a small fraction of the total cosmic energy content. The supernova observations also allowed scientists to reconstruct the history of cosmic expansion in more detail. They showed that in the early universe, expansion was slowing down due to the gravitational influence of matter. Galaxies were forming, clusters were growing, and structures were becoming more complex. However, at some point in the past, dark energy began to dominate. When this happened, the expansion of the universe shifted from deceleration to acceleration. This transition is one of the most important events in cosmic history. It marks the point where the universe changed from being matter-dominated to dark energy-dominated. Before this transition, gravity was the dominant force shaping the universe. After it, dark energy took over, controlling the large-scale evolution of space. Understanding when and how this transition occurred is a major goal of modern cosmology. By studying more distant supernovae and other cosmic signals, scientists hope to determine the exact timeline of this shift and what caused it. The discovery of cosmic acceleration also had a major impact on theoretical physics. It forced scientists to reconsider the role of vacuum energy in quantum theory. According to quantum mechanics, empty space is not truly empty. It is filled with fluctuations of energy that constantly appear and disappear. These fluctuations should contribute to the energy density of space. However, when physicists calculate the expected vacuum energy from quantum theory, the result is vastly larger than what is observed from cosmic acceleration. This discrepancy is one of the biggest unsolved problems in physics. It suggests that either our understanding of quantum vacuum energy is incorrect, or there is a mechanism that cancels most of it out. Supernova observations continue to play a key role in refining measurements of dark energy. New surveys are being conducted using advanced telescopes that can detect thousands of supernovae across different distances. These surveys aim to improve the precision of cosmic expansion measurements and test whether dark energy has changed over time. In addition to supernovae, other methods are also being used to study cosmic acceleration. These include observations of galaxy clustering, gravitational lensing, and the cosmic microwave background. Together, these methods provide independent confirmation of the accelerating universe. Despite all this progress, many questions remain unanswered. The exact nature of dark energy is still unknown. It could be a constant property of space, a dynamic field that evolves over time, or a sign that our understanding of gravity is incomplete. Each possibility has profound implications for physics and cosmology. One of the most intriguing possibilities is that dark energy might not be constant. If it changes over time, the fate of the universe could be very different from current predictions. In some scenarios, acceleration could continue forever, leading to an increasingly empty universe. In others, dark energy could weaken or reverse, potentially leading to a different cosmic outcome. Supernovae remain one of the most important tools for investigating these possibilities. By studying them across different eras of cosmic history, Scientists can trace how the expansion rate has changed and look for signs of variation in dark energy. The discovery of cosmic acceleration through supernovae is a powerful example of how careful observation can transform our understanding of the universe. What began as a study of exploding stars led to the realization that the universe is dominated by an unknown force. Supernovae continue to shine as cosmic beacons, illuminating not only distant galaxies, but also the hidden structure of space itself. Through them, we have learned that the universe is not just expanding, but accelerating toward an unknown future driven by a mysterious energy that fills all of space. As the study of dark matter and dark energy progressed, scientists began to realize that these two invisible components were not just isolated mysteries, they were deeply connected to the structure of the universe itself. Together, they shape how galaxies form, how clusters evolve, and how the largest structures in the cosmos come into existence. When we step back and look at the universe on its grandest scales, a hidden architecture emerges, a vast cosmic web that defines the distribution of everything we can see. This structure is not random. It is shaped by the interplay of gravity, dark matter, and the accelerating expansion driven by dark energy. To understand this structure, we must first look at the universe as a whole system. On the smallest scales, matter forms atoms, stars, and planets. On larger scales, stars group into galaxies. Galaxies then group into clusters, and clusters form superclusters. But even beyond these structures, the universe reveals an even larger pattern. Galaxies are not distributed evenly in space. Instead, they form long filaments, dense nodes, and vast empty regions. This arrangement is known as the cosmic web. The cosmic web is one of the most striking discoveries in modern cosmology. It shows that the universe has a large-scale structure that resembles a three-dimensional network. In this network, filaments of matter stretch across hundreds of millions of light-years, connecting massive clusters of galaxies. Between these filaments are enormous voids, regions where very little matter exists. These voids can be tens or even hundreds of millions of light-years across, making them some of the emptiest regions in the universe. This structure did not form randomly. It is the result of tiny fluctuations in the early universe that were amplified over billions of years. In the beginning, after the Big Bang, the universe was nearly uniform, but not perfectly so. There were small differences in density from one region to another. Some areas had slightly more matter, while others had slightly less. These tiny variations became the seeds of all future structure. Dark matter played a crucial role in amplifying these initial fluctuations. Because dark matter interacts primarily through gravity and not through radiation, it began to clump together earlier than ordinary matter. While normal matter was still interacting with light and radiation, dark matter was already forming gravitational structures. These early dark matter clumps created potential wells, regions of stronger gravity that would later attract ordinary matter. As the universe expanded and cooled, ordinary matter began to fall into these dark matter structures. Gas accumulated in the densest regions, eventually forming the first stars and galaxies. Over time, these structures grew larger through gravitational attraction and merging processes. Small galaxies merged into larger ones, and clusters formed from the combination of many galaxies. This process of structure formation is still ongoing today. Galaxies continue to move along dark matter filaments, slowly merging and evolving. The cosmic web is not static. It is a dynamic structure shaped by gravity over billions of years. Computer simulations have been essential in understanding this process. By modeling the evolution of the universe from its earliest moments, scientists can test how different ingredients affect structure formation. When dark matter is included in these simulations, the resulting structure closely matches what we observe in the real universe. Filaments, clusters, and voids naturally emerge from the gravitational collapse of dark matter. Without dark matter, however, simulations fail to produce the observed structure. Ordinary matter alone is not sufficient to form galaxies quickly enough or to create the complex web-like pattern seen across the cosmos. This provides strong evidence that dark matter is not optional but essential for the formation of cosmic structure. The cosmic web also helps explain why galaxies are distributed the way they are. Instead of being scattered randomly, galaxies are found along the densest parts of dark matter filaments. These filaments act like highways of gravity, guiding the motion of galaxies over cosmic time. At the intersections of filaments, where matter is most concentrated, massive galaxy clusters form. These clusters are some of the largest gravitationally bound structures in the universe. They can contain thousands of galaxies, vast amounts of hot gas, and enormous quantities of dark matter. The gravitational pull of these clusters is so strong that it can bend light from distant objects behind them, producing gravitational lensing effects. Gravitational lensing is one of the most powerful tools for studying the cosmic web. By observing how light from distant galaxies is distorted as it passes through massive structures, scientists can map the distribution of both visible and invisible matter. These maps reveal that dark matter forms a continuous network throughout the universe, closely following the structure of the cosmic web. One of the most important insights from lensing studies is that dark matter is not evenly smooth. It is clumpy, forming dense regions within filaments and clusters. These clumps act as the building blocks of structure formation. They determine where galaxies form and how they evolve over time. The interplay between dark matter and ordinary matter is essential to the structure of the universe. Dark matter provides the gravitational framework, while ordinary matter forms the visible structures within that framework. Without dark matter, galaxies would not have formed as quickly or as efficiently. Without ordinary matter, the universe would remain invisible, composed only of dark structures with no stars or light. While dark matter shapes the structure of the universe, dark energy influences its large-scale evolution. Dark energy does not cluster or form structures. Instead, it acts uniformly throughout space, affecting the expansion of the universe. As space expands, dark energy becomes more dominant, gradually overpowering the gravitational influence of matter. This has important consequences for the cosmic web. In the early universe, when matter was more dominant, gravity was able to pull structures together, forming filaments and clusters. But as dark energy became stronger, the expansion of the universe began to accelerate. This acceleration slows down the growth of new structures. Over time, It will prevent new, large-scale structures from forming. In the far future, dark energy will dominate completely. The expansion of the universe will continue accelerating, causing distant galaxies to move beyond our observable horizon. The cosmic web will still exist locally, but it will become increasingly isolated. Clusters that are not gravitationally bound will drift apart, and the large-scale structure of the universe will gradually fade from view. This future evolution shows how dark matter and dark energy work together to shape the universe across different timescales. Dark matter builds structure, while dark energy controls the ultimate fate of that structure. One creates complexity, while the other slowly limits it. The cosmic web also helps scientists understand the history of the universe. By observing structures at different distances, astronomers are effectively looking back in time. Distant galaxies and clusters show how the cosmic web looked billions of years ago. These observations reveal that the web was once more compact and denser, with structures forming more rapidly in the past. As time progresses, the influence of dark energy becomes more apparent. Structures stop growing as quickly, and expansion begins to dominate over gravitational collapse. This transition marks a shift in the balance of cosmic forces. Another important aspect of the cosmic web is the role of voids. Voids are enormous regions of space with very low matter density. They are surrounded by filaments and clusters, but contain very few galaxies. These voids are not completely empty, but they are much less dense than the surrounding structure. Voids are important because they provide information about both dark matter and dark energy. The expansion of voids is influenced by dark energy, while their boundaries are shaped by dark matter filaments. By studying voids, scientists can gain insight into how these two components interact on large scales. Observations show that voids tend to grow over time. As matter flows into surrounding filaments and clusters, voids become emptier and larger. This process is influenced by the accelerating expansion of the universe, which pushes matter away from low-density regions. The study of the cosmic web is still evolving. New surveys are mapping millions of galaxies in 3 dimensions, creating detailed maps of large-scale structure. These maps allow scientists to test cosmological models with increasing precision. They provide strong support for the idea that dark matter and dark energy are fundamental components of the universe. One of the most important challenges in this field is understanding how small-scale physics connects to large-scale structure. How do quantum fluctuations in the early universe lead to filaments stretching across hundreds of millions of light-years? How do particle properties of dark matter translate into cosmic structures? These questions connect the smallest scales of physics with the largest scales of cosmology. The cosmic web also raises deeper philosophical questions about the nature of structure and existence. The universe is not random. It has an underlying pattern shaped by invisible forces. Galaxies are not isolated islands, but part of a vast interconnected system. Everything is linked through gravity and the expansion of space. As we continue to study the cosmic web, we are not just mapping galaxies. We are uncovering the hidden architecture of the universe. This architecture is shaped by dark matter and dark energy, 2 invisible components that dominate the cosmos. In the end, the cosmic web reveals a universe that is both structured and dynamic. It shows that what we see is only a small part of a much larger system. Beneath the visible universe lies an invisible framework that determines how everything is arranged. Dark matter builds the scaffolding, dark energy stretches the fabric, and together they create the evolving structure of the cosmos. As we reach the final stage of understanding dark matter and dark energy, we arrive at a point where science meets its own limits. The universe has revealed more about itself than ever before, yet the most important components of its structure remain invisible and unexplained. What we know now is both remarkable and unsettling. The cosmos is not dominated by the matter we can see. Instead, it is shaped by unknown forces and unseen substances that govern its behavior on the largest scales. The question that naturally follows is not only what these components are, but what their existence means for the future of the universe and for our understanding of reality itself. The modern picture of the universe is built on a framework that includes ordinary matter, dark matter, and dark energy. Ordinary matter, the atoms that form stars, planets, and living beings, represents only a small fraction of the total cosmic content. Dark matter, which does not emit or interact with light, forms the gravitational backbone of galaxies and clusters. Dark energy, even more mysterious, drives the accelerated expansion of space itself. Together, these three components define everything we observe in cosmology, yet two of them remain completely unknown in their true nature. This leads to one of the most important questions in science. How complete is our understanding of the universe? In many areas of physics, progress is measured by how well theories match observations. In the case of dark matter and dark energy, the match is only partial. We can describe their effects with remarkable precision, but we cannot yet explain what they are. This separation between prediction and understanding is what makes modern cosmology both powerful and incomplete. The future of the universe depends on the balance between these invisible components. Dark matter shapes the formation of structures, while dark energy controls the expansion of space. In the early universe, dark matter played a dominant role. It allowed galaxies to form, clusters to assemble, and the cosmic web to develop. Without it, the universe would likely be smooth and structureless, with no galaxies or stars. In contrast, dark energy became dominant much later, changing the behavior of cosmic expansion and determining the long-term fate of the universe. As dark energy continues to dominate, the expansion of the universe will accelerate further. Distant galaxies will move away from us faster and faster, eventually crossing a point where their light can no longer reach us. This is not because they stop emitting light, but because space itself is expanding too quickly for light to bridge the growing distance. Over extremely long timescales, most galaxies outside our local group will disappear from view. This leads to a future universe that is dramatically different from the one we observe today. In billions of years, the night sky will become increasingly empty. The Milky Way and Andromeda galaxy may merge into a single large structure, but beyond that local region, the rest of the universe will fade into darkness. Future observers, if they exist, may see only their local galaxy group and a dark, expanding void beyond it. the large-scale structure of the universe will become invisible, not because it no longer exists, but because it has moved beyond the observable horizon. This concept raises profound questions about knowledge and observation. If future civilizations cannot observe distant galaxies, they may never discover that the universe is expanding. They may not realize that there was a Big Bang, or that the cosmos has a large-scale structure. The accelerating expansion caused by dark energy could isolate regions of the universe so completely that cosmic history becomes unobservable from within those regions. This possibility highlights how special our current moment in cosmic history is. We live at a time when the universe is still visible on large scales. We can observe distant galaxies, measure cosmic expansion, and study the structure of the cosmic web. In the far future, this opportunity may no longer exist. While dark energy shapes the ultimate fate of the universe, dark matter continues to define its structure. Every galaxy, including our own Milky Way, is embedded in a massive halo of dark matter. This halo extends far beyond the visible edge of the galaxy and contains most of its total mass. Without this invisible structure, galaxies would not remain stable. Stars in the outer regions would drift away, and spiral patterns would not hold their shape. Dark matter also plays a key role in galaxy formation. In the early universe, small fluctuations in density were amplified by gravity. Dark matter, interacting only through gravity, began clumping together before ordinary matter. These early clumps acted as gravitational seeds, pulling in gas and forming the first galaxies. Without this process, the universe would not have developed its current complexity. Despite its importance, dark matter remains undetected in laboratories. We know it exists because of its gravitational effects, but we do not know what it is made of. This creates one of the central paradoxes in modern physics. We can measure something that dominates the universe, yet we cannot observe it directly. The same is true, in an even deeper sense, for dark energy. We know it drives the expansion of the universe, but we do not know why space itself contains this energy. It may be a property of space, a quantum effect, or something entirely new. Unlike dark matter, which clusters and forms structures, dark energy is smooth and uniform, making it even more difficult to study. Together, these two unknowns define the boundaries of modern cosmology. They are not small corrections to existing theories. They are the dominant components of the universe. This means that our understanding of the cosmos is still incomplete at the most fundamental level. One of the most important goals of future research is to determine whether dark matter and dark energy are truly separate phenomena, or whether they are connected in some deeper way. Some theoretical models suggest that they may arise from a single underlying framework. In these ideas, the same fundamental physics could give rise to both gravitational structure and cosmic acceleration. If this is true, it would point toward a deeper theory that unifies all aspects of cosmology. To explore these possibilities, scientists are developing new generations of experiments and observations. Large-scale surveys of galaxies are mapping the distribution of matter across the universe with increasing precision. Space telescopes are observing distant supernovae and galaxies to measure cosmic expansion more accurately. Underground detectors are searching for rare interactions between dark matter and ordinary matter. Each of these efforts contributes to a more detailed picture of the universe. At the same time, theoretical physics is pushing into new territory. Ideas from quantum field theory, string theory, and modified gravity are being explored as possible explanations for dark matter and dark energy. These theories attempt to go beyond the standard model of particle physics and general relativity, two of the most successful theories in science, but both incomplete when applied to the full universe. One of the key challenges is that dark matter and dark energy do not behave like anything we experience in everyday life. They do not emit light, they do not form atoms or molecules, and they do not interact strongly with known particles. This makes them fundamentally different from everything we have studied in laboratories. Understanding them may require entirely new principles of physics. Despite these challenges, progress continues. Each new observation narrows the range of possibilities. Each new experiment tests the boundaries of known physics. Over time, the unknown becomes more constrained, and the path toward understanding becomes clearer, even if the destination is still far away. Beyond the scientific implications, dark matter and dark energy also change how we think about our place in the universe. The fact that most of the cosmos is invisible challenges our intuition. What we see in the night sky is only a small fraction of what exists. The structures we observe are shaped by forces we cannot directly perceive. This realization expands our understanding of reality itself. It also highlights the limitations of human perception. Our senses evolved to understand the world on Earth, not the vast scales of the cosmos. It is only through technology and mathematics that we can access the deeper structure of the universe. Telescopes, detectors, and simulations extend our vision far beyond what is naturally visible. In this sense, the study of dark matter and dark energy is also a study of human knowledge. It shows how far science can reach beyond direct experience. It reveals a universe that is both comprehensible and deeply mysterious at the same time. As we look toward the future, one of the most important questions is whether we will eventually discover the true nature of these invisible components. Will dark matter be identified as a new particle? Will dark energy be explained as a property of space, or something even more fundamental? Or will both require a complete revision of our understanding of physics? Whatever the answer, it will likely transform science at its core. Discovering the nature of dark matter would reveal a new form of matter that exists throughout the universe. Understanding dark energy would explain the fate of the cosmos itself. Together, these discoveries would complete one of the most important chapters in the history of science. Until then, we continue to observe, measure, and explore. Each new piece of data brings us closer to understanding the invisible universe. The cosmos is not silent. It speaks through gravity, through light, and through the expansion of space. We are learning to interpret this language, one discovery at a time. The story of dark matter and dark energy is not just about unknown substances. It is about the structure of reality itself. It is about how the universe is built, how it evolves, and how it will end. It is a reminder that even in a universe filled with light, the most powerful forces may remain unseen. And as science continues forward, one truth becomes increasingly clear. The universe is far more complex than it appears, and the invisible may be just as important as the visible in shaping everything that exists.